After studying this module, you shall be able to understand what is factor analysis, learn about the purpose, assumptions, uses and types of factor analysis. Learn to extract factors from correlation matrix using the Centroid method and comprehend about the methods to calculate the number of factor matrices required for a given correlation matrix. Introduction. Charles Spearman pioneered the use of factor analysis in the field of psychology and is sometimes credited with the invention of factor analysis. He discovered that school children's scores on a variety of seemingly unrelated subjects were positively correlated, which led him to postulate that a general mental ability or G underlies and shapes human cognitive performance. His postulate now enjoys broad support in the field of intelligence research, which is known as the G theory. Raymond Cattell expanded on Spearman's idea of two-factor theory of intelligence after performing his own tests and factor analysis. He used a multi-factor theory to explain intelligence. Cattell's theory addresses alternate factors in intellectual development, including motivation and psychology. Cattell also developed several mathematical methods for adjusting psychometric graphs such as his Scree test and similarity coefficients. His research led to the development of his theory of fluid and crystallized intelligence, as well as his 16 personality factors theory of personality. Cattell was a strong advocate of factor analysis and psychometrics. He believed that all theory should be derived from research, which supports the continued use of empirical observation and objective testing to study human intelligence. Factor analysis is a statistical tool to examine the interrelationships among various variables. It investigates several variables simultaneously and tries to locate them into a small number of dimensions that are referred to as factors. It is beneficial as it helps in summarization of data and identifies the latent dimensions or factors within a data set. The primary aim of the factor analysis is data reduction, and variables that are highly correlated with each other are identified as representing a single factor, and variables that do not correlate with each other are identified as representing orthogonal or independent factors. The ideal factor analysis would identify a small number of factors which are orthogonal to each other. Factor analysis and introduction. Factor analysis is a very broad term and does not really represent a unitary concept. It generally refers to a set of statistical techniques, all of function so as to locate a small number of dimensions, clusters or factors in a large set of independent variables or items. In factor analysis, a researcher starts with a large set of variables and variables that highly correlate with each other. They are identified as representing a single factor, and variables that do not correlate with each other are identified as representing orthogonal or independent factors. The ideal factor analysis would identify a small number of factors which are orthogonal to each other, that is, in spatial terms, they would lie at right angles to each other when graphed. This was suggested by Ribber and Ribber in 2001. The purpose of factor analysis. The main purpose of factor analysis is to identify the underlying structure of relationships among variables and to classify them into homogeneous groups or clusters that are referred to as factors. Data reduction as is the other purpose of factor analysis, as it decreases the number of variables and clusters them together under factors. The third purpose is to summarize and understand the data by identifying the relationships among the variables. It also serves the purpose to understand and confirm the latent variables of structural equation modeling, to remove redundancy or duplicity from a set of correlated variables, to identify and distinguish between latent variables that are called factors and observed variables within the data set. Another purpose of factor analysis is to identify the orthogonal factors that are independent of each other. Assumptions of factor analysis. Factor analysis can be performed on the data set which is usually interval in nature, that is, the measurement of the variables should be at least in interval scale of measurement. However, it can also be exercised on ordinal scale of measurement where scores are represented in Likert scale form. Variables subjected to factor analysis should be linearly correlated to each other. And another important assumption is that the variables should also exhibit moderate to high degree of correlation with each other. Uses of factor analysis. The factor analytic technique is used widely in the development of psychometric tests and scales. In this aspect, factor analysis helps in deciding the factor structure of the items in a test and also in giving the name to the concept to be measured by the test. It also helps in examining the underlying structure of psychological constructs by identifying its latent dimensions. Several theories of intelligence have been based on application of factor analysis, and as we have earlier discussed, Spearman's two-factor theory, Thurston's theory of primary mental ability, Guilford's structure of intellect model, Cattell's theory of fluid and crystallized intelligence are some of the examples that have taken help of factor analysis in developing their concepts and tests. Types of factor analysis. Depending upon the underlying assumptions, factor analysis is of two types. Exploratory factor analysis, which we refer to as EFA, and the purpose of exploratory factor analysis is to identify the total number of factors that exist for a given correlated variables. It also helps to determine the correlation between the variables and the factors in the data set. The other type of factor analysis can be confirmatory factor analysis, referred to as CFA, and the purpose of confirmatory factor analysis is to confirm or validate the priori theorized or hypothesized factor structure and its underlying variable. In this, a researcher already knows which variables are which factors. Confirmatory factor analysis forms the basis of structural equation modeling. The methods of factor analysis. The basic data that we use for factor analysis is the same for the correlation matrix when using the different procedures of analysis. Though there may be procedures that make use of the matrix of covariance, major methods that are popularly adopted for factor analysis are the Centroid method, which was developed by Thurston in 1947, summation method developed by Burt in 1941, principal axis method developed by Kelly 1935, and another one, the principal components method developed by Hoteling in 1933. For extraction of factors, the basic data required is the correlation matrix. For any correlation matrix that is derived either from the test scores or values, the diagonal cell values are empty. These cells can either hold the reliabilities of the test or the estimates of communalities or all 1.00 values. The diagonal values are all 1.00 in Hoteling's principal axis method, whereas in Thurston's centroid method, the communalities are placed in the diagonal cells of the correlation matrix. This is done to calculate the factors. The choice of the values to be used in the diagonal cells affects the number of factors extracted as well as the loadings of each factor on each test. Extraction of factors using the centroid method. In Thurston's centroid method of factor analysis, the correlation matrix is replaced by the factor matrix. A correlation matrix is square in nature, whereas where the rows and the columns are denoted by variables. Theoretically, factor matrix can be square or rectangular, but practically factor matrix is mostly rectangular. The columns represent the factors and the rows represent the variables. To understand Thurston's centroid condensation method to extract factors, let us consider a correlation matrix. Correlation matrix Rij, right? We can have a look at the figure, and the columns 1, 2, 3, 4, 5 and the rows are also 5 in number. We can see these are the correlation values which are mentioned here, right? Now, the first step is to add the values column wise and row wise and denote by a symbol C and sigma respectively to calculate the grand total. So, if we look into the figure, the columns and the rows, we find that there is one column and the bottom row which has been highlighted in yellow. The column towards the extreme right is the sum of, that is the sigma value, and the columns total is also given, and at the same time we find GT or the grand total equal to 11.34 here. The next step is to find the value of n by the formula n equal to 1 upon under root GT, right? And we find n equal to 1 upon under root 11.34, which on mathematical manipulation and calculation comes out to be 0.297. The third step is multiply each column sum with n, which we have got in step 2, to get the first factor loading L1 of each test, that is Li is equal to C into n. The first factor loadings for test 1, 2, 3, 4 and 5 have been found to be, on application of this formula, to be 0.58, 0.64, 0.62, 0.83 and 0.71 respectively. The next step is to obtain the second factor loadings. One has to find the cross product matrix. List all the first factor loadings on the horizontal and vertical side of a table. Multiply corresponding rows and columns to obtain the cross product matrix Lij, which is shown in the table. We find that when we multiply the first factor loadings with the others, this is the result that we obtain. Now, the next step is to find out the first factor residual. To find the first factor residual, subtract the first factor cross product matrix Lij from the original correlation matrix Rij that we had started with in the beginning. So, the residual matrix is equal to correlation matrix minus the cross product matrix. So, the first factor residual is to find the first factor residual, subtract the first factor cross product matrix Lij from the original correlation matrix, that is the correlation matrix we had originally started with, and we arrive at the residual matrix, that is equal to correlation matrix minus the cross product matrix. Now the table below gives us exactly the same for the next. The first factor residual is the next step. And how do we find it? To find the first factor residual, subtract the first factor cross product matrix, that is Lij, from the original correlation matrix Rij. So the residual matrix is equal to correlation matrix minus the cross product matrix. Step 6 is add values column wise and row wise to denote by the symbol C and sigma respectively to calculate the grand total. Something that we have done before in the initial steps with the original matrix. So what we have is now the sum of all the columns and sum of the rows along with the grand total, which is 0.10. The seventh step is reflection. In the above matrix that we have got, the grand total is negative, indicating the need of reflection. That is, the test vectors need to be extended in the opposite direction but maintaining their length. For each factor to account for as much variance as possible, the reflection of vectors is done so as to maximize the grand total. The method of reflection works best by inspecting the factor loadings in the residual matrix. The variables with the most negative factor loadings are reflected by changing the sign from positive to negative and vice versa, both row wise and column wise. Hence, a reflected residual matrix is obtained. Since the variables 3, 4 and 5 in the above residual matrix need reflection, therefore, the reflected residual matrix is in the table, right? And you can see that the variables 3, 4 and 5 have been marked with a star to indicate that these have been reflected and they had negative values, because of which reflection procedure was followed. So what do we arrive? We arrive at the totals once again, and this time the grand total is found to be 2.22. The next step is to find out the second factor loadings. The second factor loadings are calculated in a similar way as for the first factor loadings, that is, we exactly follow the steps that we had done in step 1, 2 and 3, and we find the grand total 2.22. N is equal to 1 upon square root of 2.22, which turns out to be, upon calculation, to be 0.67. The second factor loadings are 0.46, 0.30, 0.28 and 0.18 and 0.28. The second factor loadings are obtained. The variables that were reflected are reflected back to their original signs, and hence the second factor loadings are 0.46, 0.30, minus 0.28, minus 0.18 and minus 0.28 again. A similar method could be continued with the residual matrix and not the reflected residual matrix for third, fourth, nth factor extraction. Hence, once the obtained factor matrix is factor 1 for tests 1, 2, 3 and 4, 0.58, 0.64, 0.62, 0.83 and factor 2, 0.46, 0.30, minus 0.28 and minus 0.18. One important question is how many factors can be extracted while applying factor analysis to a data. Let us explore that problem also. How many factors to extract? In theory, the maximum number of factors that can be extracted from a set of correlation coefficients is equal to the number of variables or tests involved. For example, for a 10 into 10 correlation matrix, the maximum number of factors that can be extracted are 10. But the principle of factor analysis, as we remember, is to extract the common variance that can account for maximum variance. So, it becomes vital to decide the number of factors that can be extracted for a specific research problem. The following three methods help us to understand how many factors can be extracted for the research problems. These methods, which help us in deciding how many factors have to be extracted from a given set of data, are Factor formula, Eigenvalue index and residual correlation matrix. Let us explore each one of them and see what is the importance and application of each to the factor analytic method. The Factor formula. Factor proposed the formula to decipher the number of factors that can be extracted for a research problem. The formula is that number of factors should be equal to 2n plus 1 minus under root of 8n plus 1 divided by 2. Now, on application of this formula, we can arrive at the number of factors that should be ideally expected from a correlation matrix, and they should be extracted. Now, in this formula, n is equal to the number of variables in the correlation matrix. Let us have an illustration of this formula also, and let us take a problem. Suppose we have to identify the number of factors that can be extracted in a research problem which has 15 variables. The solution, of course, upon application of the formula is number of factors is equal to 2n plus 1 minus square root of 8n plus 1 divided by 2. Now, here as n is equal to 15, upon the substitution of the values in the formula, we find that the total number of factors that can be extracted from a 15 variable correlation matrix is 10.525 and rounded up to 11 factors. So, maximum of 11 factors can be extracted with a 15 variable correlation matrix. Hence, in a research problem with 15 variables, 11 factors are important to be extracted. The other method that help us in deciding how many factors to be extracted is the eigenvalue index. The number of factors that have to be extracted can be determined by calculating the eigenvalue index for each factor till an eigenvalue of 1 is obtained. That is, those factors are to be extracted whose eigenvalues are either 1 or more than 1. Factors with eigenvalue less than 1 are not considered for contributing to the variance and hence are not given importance at all. The statistical package for social science, that is SPSS, makes use of this method when extracting factors. Let us have an illustration of this method also and determine the number of factors that can be extracted on the basis of eigenvalues of the factors. We have 4 factors lined up here for the variables and the values are given here. Now, the solution to the problem here is eigenvalue of factor 1 is square all the values and add them, and it turns out to be 3.466. Eigenvalue for factor 2 is 1.800. For factor 3, the eigenvalue turns out to be 0.70. Eigenvalue for factor 4 is 0.39, and since only these factors are accounted for whose eigenvalue is 1 or more than 1, therefore only factor 1 and factor 2 will be extracted. Hence, only 2 factors can be extracted for this correlation matrix from which the eigenvalues have been taken, and the remaining factors according to the eigenvalue criteria or method are not suitable for factor analytic study. Third method that can be used for deciding how many factors to be extracted for a given data is the residual correlation matrix method. The residual correlation matrix is the third method by which one can decide when to stop extraction of factors for a given research problem. In this method, it is observed that when most of the correlation coefficients, that is more than 50% of the correlation coefficients in the residual correlation matrix are 0 or approaching 0, then one should stop further extraction of factors. Factor extraction will be continued in the following kind of residual correlation matrix. We have the matrix given, and in the following residual correlation matrix, further factor extraction will be stopped as most of the correlation coefficients are either 0 or approaching 0. Let us have a look at the matrix again, and we find that it is really true. Many values are in negative or approaching 0, right? In the following residual correlation matrix, further factor extraction should be stopped. Summary of factor analysis. Factor analysis is a statistical method used to describe variability among observed or correlated variables in terms of a potentially lower number of unobserved variables called factors. For example, it is possible that variation in 4 observed variables mainly reflect the variations in 2 unobserved variables. Factor analysis searches for joint variations in response to unobserved latent variables. The observed variables are modeled as linear combinations of the potential factors plus error terms. The information gained about the interdependency between observed variables can be used later to reduce the set of variables in a data set. Computationally, this technique is equivalent to low rank approximation of the matrix of observed variables. Factor analysis originated in psychometrics and is used in behavioral sciences, social sciences, marketing, product management, operations design and operation research, and other applied sciences that deal with large quantities of data. Factor analysis is related to principal component analysis (PCA), but the two are not identical. Latent variable models, including factor analysis, use regression modeling techniques to test hypotheses, producing error terms, whereas the principal component analysis is a descriptive statistical technique. There has been significant controversy in the field over the equivalence or otherwise of the two techniques, and one can refer to exploratory factor analysis versus principal component analysis data and understand the differences between the two. The primary distinctive element of factor analysis is data reduction. Variables that correlate highly with each other represent a single factor, and the variables that do not correlate with each other are identified as representing independent or orthogonal factors. The centroid condensation method of factor extraction involves calculation of the grand total by adding the correlation coefficients of each column. This total is then used to calculate capital N, which is multiplied with each column sum so as to obtain the first factor loadings of each test. This, a cross product matrix is obtained that is subtracted from the correlation matrix to obtain the residual correlation matrix. The residual correlation matrix may have to be reflected so as to maximize the grand total of the matrix. This is done by changing the signs of the factor loadings in the residual matrix from positive to negative or vice versa. For the variables, both row wise as well as column wise, the second factor loadings are then calculated from the reflected residual factor loadings, and they are reflected back to their original signs also. Further factor loadings may be obtained in a similar way. The decision about the number of common factors to extract and retain must steer between the extremes of losing too much information about the original variables on one hand and being left with too many factors on the other. Now this has to be decided judiciously, and we have seen there are a number of methods available for it. We have also studied them. Various criteria have been suggested to understand the number of factors that can be extracted. Some of them are the Fructo formula method, the eigenvalue index method, and the residual correlation matrix method.